Let's finish this first chapter with what is arguably one of the most important results in probability theory. It's called Bayes' theorem. If you have an experiment and it generates outcomes, you're often interested in determining the probability that a certain condition was present given the outcome. Or say, the probability that a specific hypothesis was valid given the data that you observed. So we've already noted if the probability of, say, events A and B are both non-zero, which is to say their product is non-zero, that you can write the intersection, the probability of the intersection, in two different ways, right? You can sort of basically view it as the probability of A intersection B being the product of the probability of A by the probability of B given A. In fact, you obtain that simply by using the definition of the conditional probability and rearranging the terms. But whether you look at A intersection B or B intersection A, that's the same set, that's the same intersection, that's the same event. And so you can also write it as the probability of B times the probability of A given B. These two things have to be equal. Well, if you can rearrange the terms, for instance, if you take this term right here and you send it down at the denominator, you get what is known as Bayes' theorem. The probability of A given B would be the probability of B given A times the probability of A divided by the probability of B. And that's a simple corollary of the axioms of probability that we've seen. There's nothing fundamentally difficult to understand about this theorem, and yet it has far-reaching consequences. If you recast it as part of a central data analysis question, you can perhaps see a little bit more easily what its true importance is. When you run scientific experiments or even engineering experiments, what you're trying to ascertain is that given everything that you know before you run your experiment, does the data that you collect, does the data that you observe support or potentially invalidate a hypothesis that you had in mind? That's what the scientific method says. You say, I think this is true, I'm going to try to falsify the hypothesis, and I'm going to run an experiment to collect data to see if I can support a hypothesis that I'd really like to support. The problem is that it is very difficult to compute this directly. The probability that the hypothesis is true given the data, that is not an easy thing to compute. If you're lucky, you might be able to use Bayes' theorem to recast, as I said, the probability that you're trying to compute. So when you want to compute the probability that the hypothesis is true given the data that you've observed, instead you might actually compute the probability that you would observe the data if the hypothesis was true, and you multiply that by the probability that the hypothesis is true divided by the probability of observing the data, independently of whether the hypothesis is true or not. In many instances, we do not need this denominator here. It's the same for all hypotheses that you're testing. So it's a constant. We often remove it, omit it from the formula here. And so one of the ways in which you can write Bayes' theorem is this one here. The probability that the hypothesis is true given the data that you observed is proportional to the probability that you would observe the data given the hypothesis times the probability that the hypothesis is true. And your hope is that this combination of terms is easier to compute. Well, in the vernacular, when you do Bayesian analysis, these are the terms that you use. The probability that the hypothesis is true, that's the probability that it is true prior to the experiment. You know, using all the background info you have at your disposal. We call that the prior probability, or just the prior. The probability that the hypothesis is true given the data that you've observed, that's called the posterior probability. That is what you are trying to compute. The probability that the data will be observed if the hypothesis is true, that's called the likelihood. Later on, we'll do regression analysis. One of the things we'll see is how to compute the likelihood. So when people talk about Bayes' theorem, they will often say that the posterior is proportional to the likelihood times the prior. Another way to say this is that you update your beliefs in the presence of new information. So the priors are your beliefs. The likelihood is the new information, the new data that you have, and the product of the likelihood and the prior gives you a new posterior distribution. You've updated your belief about a situation. Now the prior is quite important. Let's say, for instance, if you're trying to determine the true shape of the Earth, and your hypothesis is that the Earth is flat. Now, if you're going to use Bayes' theorem, you need to have the probability that you would observe whatever data you observe whenever you run whatever experiment you want if the Earth is flat, times the probability that the Earth is flat. And that gives you a product, which is a posterior distribution, the probability that the Earth is flat given the data that you observed. Now you can run any experiment you want. If you have zero belief in the Earth being flat, you'll be multiplying the likelihood by 0, which gives you 0. So when you are absolutely 100% certain about a hypothesis, no amount of information can change your mind in the Bayesian framework. I'm not saying that you be right or wrong about your ideas about whether the Earth is flat or not, but I happen to think with 100% certainty that the Earth is not flat. So it doesn't matter what experiment you run, my posterior will not have changed from that original degree of belief. But if there was even a slight probability that the Earth could be flat, in my mind, slight probability that the belief that the Earth is flat would not be wrong, then conceivably some data could end up swaying me. Now, that belief would be very slight, the probability of the Earth being flat. So I would need a lot of evidence, a lot of data to sway me. And the data would have to be good data. It's not enough to have a lot of data. If the data doesn't support the conclusion that the Earth is flat, then you're not really helping somebody change their minds by showing them the data. But at least it is conceivable that my opinion could be changed if there was any room for doubt. But I have no room for doubt. So it doesn't matter what data you have. Okay? My belief in the flatness of the Earth will not be changed by the data that you have. If you only have two events here, A and B, and they're both non-empirical, empty events, which is to say they both have a non-zero probability, then you can rewrite Bayes' theorem and you basically expand the denominator. The probability of B will be actually written as the probability of B given A times the probability of A plus the probability of B given the complement of A or not A times the probability of not A. That's the law of total probability. Now this generalizes, of course, if you have more than two events. As long as all these events are mutually exclusive and cover all possibilities, so mutually exclusive and exhaustive, then you can write Bayes' theorem as follows. The probability of AI given B would be the probability of B given AI times the probability of AI divided by the probability of B. And again, you use the law of total probability here to have a denominator, which is, well, each of the terms in the denominator here has the same form as the term in the numerator. So this is a nice natural way to write Bayes' theorem. Let's see what it looks like in action. In 1999, there were three types of Nissans that were being sold in North America. We had a Sentra, a Maxima, and a Pathfinder. So we'll denote those by S, M, and PA. I use PA instead of P because P is reserved for probability, and I didn't want there to be confusion, but usually you pick the first letter. Of all the vehicles that were sold by Nissan in North America, 50% of them were Sentras, 30% were Maximas, and 20% were Pathfinders. Simultaneously, that year, 12% of the Sentras, 15% of the Maxima, and 25% of the Pathfinder had a specific defect, D. What the defect here is not important, just there was one. So here's a question for you. If you own a 1999 Nissan, what's the probability that it has the defect? The way this is spoken or said screams we should be using the law of total probability because it doesn't specify which of the three models you own. If you're going to use conditional probability, the probability that you have a Sentra would be 50%. Because 50% of vehicles were Sentras. The probability that it's a Maxima, 30%, because 30% were Maximas. And the probability that you have a Pathfinder, 20%, because 20% were Pathfinders. That adds up to 100%. What we have here are exhaustive events. Are they mutually exclusive? Well, it's conceivable that you could have more than one Nissan vehicle. But we're looking at a specific vehicle. So even if you have two, we're looking at one of your vehicles here. And it's impossible for a vehicle to both be a Sentra and a Maxima, or a Maxima and a Pathfinder, or a Sentra and a Pathfinder. So these events are mutually exclusive and exhaustive. What's the probability that you have a defect? Well, that depends on what type of car you actually have. The probability of a defect, if you own a Sentra, that should be 12%, because 12% of the Sentras have the defect. Same thing for the probability of D given M, probability of D given PA. These numbers are given to us. 12, 15%, 25%. Okay, and now we have all the information that we need. We use the law of total probability. The probability of a defect is the conditional probability of a defect if you have a centra times the probability that you have a centra plus the probability of a defect if you have a maxima times the probability of the maxima plus the probability of a defect if you have a pathfinder times the probability of a pathfinder. You just plug in the numbers, add them all up, and you'll get 15.5%. Now, does that sort of make sense? Well, look, 12% of the centras had the defect, 15% of the maximas had the defect, so 15.5 is reasonable. 25% of the pathfinders had a defect. Now, 15.5 is substantially smaller than 25%, but you keep in mind that the pathfinders were the least popular of the models. They only make up 20% of the full space. Another way to look at this would be to say, look, here's all the centras, all the Nissans, that were sold. I have 50% are centras, 30% are maximas, and 20% are pathfinders. And what we have is that 12% of the centras, roughly speaking, this could be easier, these are defective. That 15% of the maximas are defective, and then I'm just saying 25% here. Let's pretend that my drawings are up to scale. They're not. What you're interested in is computing the area of the red region, red zone. And this is what the law of total probability really does for you. Now let's assume that the Nissan that you have has a defect. Which model are you most likely to own? In the first part, you computed the total probability, the denominator in Bayes' theorem, the probability of the defect. Here, what you're going to do is you're going to compare the posterior probabilities. What's the probability that the maxima has the defect? Sorry, let me rephrase that. What's the probability that you have a maxima if it has a defect, or that you have a centra if it has a defect, or that it's a pathfinder if you have a defect? You're not interested in the prior. You're not interested in the probability of M, of S, or of PA. You're interested in these probabilities given that a defect has been observed. So the numbers don't change for the most part. 12%, 50%, 15%, 3%, 25%, 20%. These are all numbers that we've obtained previously. And then you divide that by the probability of having a defect. And using Bayes' theorem, you can compute the exact probability that you're interested in. So it's important here to realize that you want to find these probabilities, these posteriors, and you can compute them not directly, that's actually impossible to do, but if you use Bayes' theorem, and you flip the conditional probability, multiply by the prior and divided by probability of the defect, then you can obtain some idea as to which car it is that you own. And based on this, you would say it is likely that the car you own is a centra if it has a defect. I mean, it could also be the maxima, it could also be the pathfinder, but it's most likely to be the centra. And this might be counterintuitive because the centras were the least likely to have the defect. Only 12% of them had the defect. It's just that they're so prevalent in the population that if you have a defective car, it is still most likely to be a centra. The example you often see in these courses is something like the following. is a test for a particular disease, and let's say it has a very high success rate. If the patient has a disease, the test will report a positive with probability 99%. So it's 99% accurate for positive results. And if you don't have the disease, the test will report that it's negative with probability 95%. So it's slightly more accurate for positive cases than for negative cases. That happens. Now let's suppose that only 0.1% of the population has the disease. I don't mean 10% here, 0.1%. So a very small prevalence. What's the probability that you have what's the probability that you do not have the disease if you test positive? In other words, how worried should you be if your test is positive? So we'll say that the event that the patient has a disease is D, and A will be the event that the test is positive. So you're interested in computing the probability of having the disease if the test is positive. Well, that's not the one we want right away, but eventually we'll use that number to compute the answer to the question that we have in mind. So that's the probability of a true positive, in a sense. Now we use Bayes' theorem together with the law of total probability. It is simple. All we really need to do is to compute the right probabilities. So what are the things we need to know how to compute, or we need to have information on? We need to compute the probability that the test is positive given that you have the disease. But we know what that number is. That's the 99% here. That's the accuracy. And we're lucky this thing shows up twice. It shows up here, shows up here. Then we need to know the probability of having the disease. Well, we know what the probability is. It's 0.1%. It shows up here, shows up here. Okay, now we need to know the probability of the event coming up, the probability of the test coming up positive if you do not have the disease. Well, we can compute that as well. We know that if you do not have the disease, the test will report a negative with probability 95%, which means that it will report a positive with probability 5%. And finally, we need to know the probability of not having the disease. Well, the probability of having the disease is 0.1%. So this number here, this. We put all these numbers together, we just add them up, do the products, and we get 0.019. So if you test positive for a disease with such a low prevalence, there's still only about a 2% chance that you truly have the disease, based on the accuracy rates that are being given here. It sounds like it's not a lot, and it isn't. The 2% chance is not great, but keep in mind that it's about 20 times larger as a probability than what your prior was. Originally, if you knew nothing else, you would have assumed that somebody has the disease 0.1% of the time. Here, the presence of a positive test boosts this probability to 2%. Still low in absolute terms, but high in relative terms. Like, the test seems to be very accurate. fact it is, like 99% and 95%. These are high accuracies. But the incidence is very, very low, so that the vast majority of patients who do test positive don't have the disease. When you're working with probabilities, you need to take both the likelihood and the prevalence into account. It is not sufficient to just look at the likelihood, as this example here showcases. We'll finish this with a very famous example, the Monty Hall problem. You're probably too young to know this or remember this, but when I was a kid, the internet didn't exist, or at least it wasn't something that you and I could just go on and surf. And once these message boards started popping up, the first flame wars were about politics, obviously, and religion, also obviously, but there was a fair number of people who used to fight about the Monty Hall problem. The setup is the following. Let's say you're on a game show, and you're given the choice of 3 doors. The doors are closed, you can't see what's behind them, but you know that behind one of them there's a prize, and behind the other 2 there's, like, I don't know, heaps of rubbish, so something you don't want. You pick one of the doors. Say you've picked door number 1. This one right here. It's your first pick. The host, they can tell what's behind the doors. They will open one of the other 2 doors. The door they open will be the door behind which the rubbish heap is found. So now you, as the contestant, still have 3 doors in front of you. One of them has been opened and you have access to see what's behind it. You see the actual anti-prize. You know which door you've selected. It would have been this one. If you want to switch, you can. Or you can keep the door that you have. Should you switch? What is your strategy at this point? And then the fights are starting and people would say it doesn't matter whether you switch or not. I mean, you're just as likely to get the prize as you are to get the anti-prize. There's a 50-50 chance. You might as well stay where you are, right? S is going to be the event that switching to another door is a successful strategy. And D will be the event that the prize was behind the original door that you had selected. So we're going to look at the game where we're going to modify the game a little bit. The first game we look at, the host opens no door for you. So you pick a door, and then you're offered the opportunity to switch from the door you'd picked to any one of the other 2 doors, but no door is open in the process, so you don't have access to external information. What's the probability that switching to another door would actually be a successful strategy? Well, if the prize was behind the door you had originally selected, switching would be a failing strategy. It would succeed 0% of the time. So if the prize was behind the original door, switching is a losing strategy. The probability of it being successful, if the prize was originally behind the first door you've picked, that would be 0. Now, what's the prior probability that the prize would be found behind the door you originally selected? It's about 33%. Here we're assuming that there isn't some sort of weird weird setup that would make these probabilities not be 33%. Now, if the prize was not behind the original door, and these are your only two options, either the prize was behind the original door or it wasn't, and we've just taken care of the case where the prize was behind the original door. So now let's assume that it was not behind the original door. When you switch, then, you have a 50-50 chance of being successful. And so the probability that the switching is successful if the prize was not behind the original door would be 50%. And the prior for that is 2/3. Because there's 67% chance that the prize would not have been behind the original door you selected. And here you flat out just use the law of total probability. We're not yet at the Bayesian bit. The probability that the strategy is successful would be the probability that it is successful if the original door hid the prize, times the probability that the original door hid the prize. But we know this is 0. This whole thing here is 0, and we're left with the probability that the strategy of switching was successful if the prize was not behind the original door, times the probability that the prize was not behind the original door, and that gives you a total of 33%. So in this case, what you get is probability that switching would be successful would be 33%. In which case, you might as well stay where you are. Now we're going to look at the case where the host actually opens one of the other two doors. So something has changed here. Even though at first glance it looks like nothing is really changing, you now have more information at your disposal. If the prize is behind the original door, switching would succeed still 0% of the time. Because if you switch, you've lost your ability to win the prize. So that hasn't changed. And the prior for the prize being behind the original door is 1/3. So this information hasn't changed at all. It's the same setup as the original. If the prize is not behind the original door, now this is something that changes. Switching would succeed 100% of the time because let's say you had originally picked this one, this is the door that they open, well, switching would work. And there isn't another option where it wouldn't make sense, wouldn't work. So you'd have 100% success if you do switch when a door is open. The act of opening the door basically restricts your options and makes it so that originally you had a 50% chance of success if you were switching if no door was open. But now that a door is open, you've removed that door as one of your options. And switching in that specific case, where the prize is not behind the original door, would actually lead to success 100% of the time. The problem, of course, is you don't know which one of these two cases you find yourself in. And the prior is still 2/3 because there was 67% chance that the prize would not have been behind the door you had selected originally. You end up with then this bit, probability of switching. Well, we plug in the numbers. This is 0. Doesn't matter what this is, this whole thing will be 0. And then you're left with this probability being 1. That's different. It used to be 1/2. Now it's 1. This probability is 2/3. That hasn't changed. And the overall probability of switching being successful is now 67%. If no door is open, switching is not a winning strategy, resulting in success only 33% of the time. But opening the door actually changes the situation. Switching becomes the winning strategy, and you'll be successful 67% of the time. If you don't believe me, the best way to convince yourself, presumably, would be to write a little bit of code that simulates the situation. And then you will see, roughly speaking, 2/3 of the time, switching will make you win. But not switching, will make you lose.